You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs for the Future Tech Podcast. I have Eliu Huerta. He's part of the Gravity Group at the National Center for Supercomputing Applications at the University of Illinois at Urbana-Champaign. So, Eliu, thanks for coming. How are you doing today?
Very good. Thanks for the invitation.
Yeah, tell me about the work that you do. What does it involve?
So just to give you some background, I am a theoretical astrophysicist by training, and the type of work that I do has to do with studying the universe through gravitational wave observations. And gravitational waves are produced when, for example, two black holes collide or two neutron stars collide. And to give you a sense of what a neutron star is, this is a star that has about the mass of the sun but concentrated in a radius that is about the size of New York City. So when these objects smash into each other, they produce this form of radiation that we call gravitational waves. We cannot see it, but we can sense it with interferometers here on the Earth. And I have been studying this type of sources for quite some time now. And I think the reason why we are talking today is because while a lot of the work to explore this type of astrophysical events has been with traditional approaches in terms of signal processing techniques and computational resources, it is in my group that we pioneered the use of artificial intelligence to accelerate this type of analysis and to observe gravitational wave sources that, due to their complexity and the type of signals that they emit, they are not easy to catch with traditional signal processing algorithms. But it turns out, based on the results that we have been presenting to the scientific community, deep learning provides the means to explore new physics, to do this analysis much faster and with minimal computational resources.
I have a quick question here.
Yep.
You know, obviously I'm on Earth here, and Earth has gravity, and it's keeping me on the ground. But how is gravitational force transmitted by matter? And why is a gravity wave, in order to be observed, require such a cataclysmic event?
Right.
Again, I know these are some basic questions, but
no, these are excellent questions. And you may know that back in the day when Einstein presented his theory of general relativity, they did not know about the existence of black holes or neutron stars for that matter. And so he did some calculations assuming that stars similar to our sun would collide somewhere in the universe, and they would produce as well gravitational waves. But he found that given the physical properties of these stars, the signature, the amplitude, or if you want, the intensity of this signal would be so small that there was no chance in the world that with technology back in the early 1910s or 1920s, people would be able to detect gravitational waves. You need objects that are super compact. In the case of black holes, they have all these matter that collapsed into a singularity that is hidden behind a horizon in a very small amount of space. So it is this type of compact objects that when they collide, they produce these bursts of gravitational waves that now we can detect. So you need some extreme circumstances or astrophysical scenarios to produce gravitational waves that we can detect here on Earth. And it just happens, it is great that the type of astrophysical events that the Laser Interferometer Gravitational Wave Observatories here in the US and the Virgo detector in Europe, they are designed to see gravitational waves with frequencies between 10 hertz and about 10,000 hertz. And this is, in somewhere in the range where we can hear things. And so the idea when they constructed these observatories is that they would measure changes in the physical properties of laser beams. And these gravitational waves introduce some very small changes in the length of the arms that host these laser beams. And by measuring these small changes is how we can infer the existence of gravitational waves. So the changes, just to give you a sense, is about 1 part in 10 to the 22 or 10 to the 21. It is much smaller than the radius of a proton. But these technologies that have been developed over the last many decades, 3 or 4 decades, now are sensitive enough such that we are now observing with a cadence of about one every month, one black hole collision in the nearby universe. And this is now a common occurrence. In the past, obviously, Einstein did not imagine that this could happen, but we are at the point where observing black hole collisions is a common occurrence. It's really outstanding.
So does matter normally transmit gravitation through gravitational waves, or how does normal gravitation work, and not in these extreme circumstances?
So gravitational waves, the same as electromagnetic waves, propagate through vacuum, right? So sound, for example, as we know it here on Earth, if you knock on a door, then there you see how sound is transmitted, or if you speak, then there is air through which the sound is going to propagate. You need a medium, right? But in the case of gravitational waves or electromagnetic waves like light, they propagate through vacuum. Mhm. So that
Okay,
is the
so
medium.
but again, how does normal gravitation work? Do we know how matter attracts other matter? How does normal gravity happen? And then I
Yes,
want to extrapolate to this other stuff. But
yeah. So the fabric of space-time is the medium through which these interactions propagate, and this is a big question that obviously Newton had back in the day. What causes gravity? What is gravity? And in his theory, he said that it was a form of sort of force that acts at uh, basically infinite speed. It propagates immediately. So the effects that the gravity has on an apple on the earth and the apple on the earth on the apple and vice versa acts immediately upon the two objects. And that is not true. I mean, information takes some time to travel. And so Einstein later on, what he found in his theory is that there is a correspondence that is dynamic. Matter tells space-time the shape that it should have, and then space-time tells matter how to move. So it is a dynamic correspondence, right? And so a manifestation of gravity is the curvature of space-time. They may sound a little bit abstract, but the typical example is you have a sheet and you put an orange in the middle of it, and you see how the sheet deforms based on the gravity of the orange that you have in the middle of it. And if you draw a marble on that sheet, then it is going to follow a shape that is determined by the orange, right? So it is similar.
right, okay.
It is a distribution of matter that determines the shape of space-time. And then space-time is also telling matter how it is going to move around it. But it is a dynamical process. It is not that space-time now is static. It is, in constant motion. And this is one of the big things in general relativity. When you try to study the collision of black holes, one of the big things is that when you solve these complex equations, it is a dynamic interaction between the two space-time and the objects that are embedded in it.
So what is a gravity wave then? It's like an electromagnetic wave that goes through the vacuum, but why does it happen, and what is the consequence of it? What does it do to space time as it travels through it? Anything significant, or it's just a slight ripple? And what can we do with this knowledge?
Again, excellent questions. Electromagnetic and gravitational waves are very different in their nature. So we know that, for example, light can be absorbed, it can be reflected, it can be lensed. So if you have light coming from a very distant star, it is possible that that light will be scattered and it will be difficult to observe, right? On the other hand, what happens to gravitational waves has been one of the keys to discover them. And the main aspects of them is that they interact very weakly with matter. They are not absorbed. They can be redshifted, that's for sure. But whatever information these waves have when black holes are merging or coalescing or colliding, all that information that is contained in these gravitational waves propagates freely from that, cataclysmic scenario all the way to the Earth. So there is no loss of information. In different words, since these gravitational waves tell us what is the nature of the space-time around these objects and the properties of the black holes that generated these waves, if we are able to measure them, then we can infer the masses of the black holes, how fast they were spinning, what are the properties of the black hole that is formed after the collision, and even get some information about the astrophysical environment where this collision happens. For example, if we infer that the properties of the orbit of the black holes are pretty much quasi-circular, then this means that the black holes were in isolation. There were not many stars or other black holes around them. But if it just happens that the orbits are more or less elliptical or eccentric, then we do know that this event happens surrounded by many other objects. So this is very important because when we want to understand the astrophysical channels that lead to the formation of black holes, we then say that either they form in a dense stellar environment or they form in isolation. And trying to figure this out is going to be one of the big themes in astrophysics in the next few years.
So we gravitational waves only come from colliding neutron stars or colliding black holes, not just from a black hole itself as material falls into it. There's no gravitational waves emitted.
So if you, for example, have a neutron star, an isolated neutron star, it has no companion, but the star has a starquake, the simile of an earthquake. That starquake can produce gravitational waves. Or if there is a readjustment of matter in the neutron star, that will produce gravitational waves. If you have a black hole in isolation and it is not perturbed, then it will not emit gravitational waves. There are other events that can emit gravitational waves, for example, core collapse supernova, which is the explosion of a star, that produces gravitational waves, that produces electromagnetic waves and also neutrinos. And people are looking, very enthusiastically for this type of sources in the galaxy because they are part of something we call multi-messenger astrophysics. Because you can feel the explosion when you detect the neutrinos, you can hear the explosion in gravitational waves, and you can see the explosion in electromagnetic waves. And having these three different cosmic messengers, if you want, gives you complementary information about these astrophysical sources. So, even shaking your fist produces gravitational waves, but they are so weak that it will be really hard to detect them. Basically, any acceleration of matter can produce gravitational waves, but it is only when it involves a lot of matter that is quite compact that produces a measurable signature of gravitational waves.
What is the point of gravitational waves? Is it to allow matter to achieve a more stable state, a lower energy state? Or is it a release of pressure from some cataclysmic events? Or, what is the purpose of gravitational waves, do you think?
Yeah. So what you find when you study the motion of two objects in general relativity is that when you have systems, for example, similar to the planetary system that we have, the Earth and the Sun, if you follow the motion of the two objects, you do not see after millions of years that suddenly the Earth now is in a spiral trajectory to fall onto the Sun, right? Uh, they have more or less very stable orbits. Okay. On the other hand, when you study the two-body motion in general relativity, again talking about objects like black holes or neutron stars, what you find is that when they are close enough to give you like some form of idea, if you had two black holes whose orbital separation was about the width of the solar system, then what we would see is that now the objects start to follow a trajectory in which there is emission of these gravitational waves. And it just turns out that these gravitational waves carry energy, angular momentum, and linear momentum. So if the system is losing energy, that now translates into an orbit that is shrinking. So they get closer and closer and closer together. And then as they get closer and closer, the emission of gravitational waves is now more intense until finally this emission drives the system to merger. So it is a different form of dynamics. It is not something that we are used to because we see planets and stars and they are not merging into each other, right? But when you have extreme gravitational fields, then it's a different ballgame. And what is the purpose of gravitational waves? Well, it just happens that when black holes collide, most of the time they do not emit light. And for centuries we have been using telescopes to observe the light or the electromagnetic waves that are emitted by astrophysical processes in the universe. So it was not until 2015 that the LIGO detectors were finally able to open the gravitational wave spectrum, and we saw in high fidelity the collision of two black holes. They did not emit light, it was just gravitational waves. And it is a remarkable event because for the first time we saw something that required no light or neutrinos, which were the messengers that we used in the past.
Is there any possible interaction with or elucidation of what dark matter is because of gravity waves?
Well, gravitational waves, as I said before, are weakly interacting with matter. So I think the connection that people have been trying to make here with dark matter is whether black holes are really behind what dark matter is. But one thing is that you do not emit light and therefore you are considered dark. And one different thing is dark matter that is not going to produce gravitational waves. These are two different things, right? We need to be careful with not combining the two. Now, it is true that some people believe that some black holes can be contributors to what dark matter is. And, well, if these black holes collide, obviously they will produce gravitational waves.
What about just a black hole itself that's sitting there spinning and eating stuff? Does it produce gravitational waves that can be observed, or they're still too low of a magnitude in order to observe them?
So that's a really interesting question. If you have one of these supermassive black holes, like similar to the ones we have in the center of the galaxy, and they are accreting matter, then they are going to emit electromagnetic radiation, X-rays, gamma rays, etc. Now, these black holes are not in isolation. They have a lot of stellar mass black holes around them. They have a lot of neutron stars around them. And there is a mission that is going to hopefully start in the mid-2030s that is called the I think it is Laser Interferometer Space-Based Antenna, LISA. And in the frequency range that this is going to be operating, we will be able to see the collision of these neutron stars and supermassive black holes, and these 10, 15 solar mass black holes with these 10 to the 6, 10 to the 8, 10 to the 7 solar mass black holes. And these will produce gravitational waves in a different frequency domain to LIGO, but nonetheless observable. So yes, these black holes, supermassive black holes surrounded by small objects, you can also see gravitational waves emanating from them when these small objects fall into them and they emit gravitational waves.
Yeah, I think that'll be cool because then maybe you can combine like the pictures of the M87 black hole and also look at the gravitational waves it emits and maybe get a much clearer picture of what that one or any other particular black hole is doing.
Absolutely. And the beauty of this is that with LIGO, we get to observe these mergers for about a few fractions of a second or a few seconds. But these other processes where you have, for example, a neutron star that is slowly spiraling into this supermassive black hole, we will be able to see those processes for about a year, if not more. And so you will be able to map with exquisite precision the structure of space-time around these supermassive black holes.
Any idea of have you ever been able to get a visual idea of what the warping of space-time looks like? Is there any way to picture it?
The warping of space-time. Well, let me tell you, this movie, Interstellar, that was, I think, co-directed by Kip Thorne, you can get a pretty good idea there.
It was weird. The movie was very disturbing to me for some reason. I don't know if you loved it or not, but it bothered me. Every time I see movies about space, I always get more and more afraid of space. I don't know why. It just seems very spooky.
As we were talking before, when you consider these extreme gravitational fields, now things that are like second nature to us are not that easy to interpret.
So, any other information that you've gotten from gravitational waves that was surprising? That now that we're seeing them regularly, is there anything new or interesting or unusual that we're learning about them?
So there are a few things that we want to learn from the black holes. One of them is, as I was mentioning before, what are the astrophysical mechanisms that lead to the formation of black holes? Is it just stars that eventually exhaust their nuclear fuel, they form black holes, and then these guys eventually get gravitationally bound with other black holes? Or are these really primordial black holes? Other questions that we want to ask, for example, in the case of neutron stars, very open questions. What is the nature of matter in these neutron stars? Well, we just do not know. And as we get more and more detections, then we can do some statistical analysis and try to infer what is the composition of matter in these super dense systems. We basically do not have the capability to reproduce in labs here on Earth this type of extreme conditions for matter. So that is something super exciting that we want to figure out in the near future. And in the galaxy, we get about 1 or 2 supernova per century, this explosion of stars. And I hope we are getting close to the next one because we do not understand very well the processes that lead to the explosion of these stars. And we have made a lot of progress theoretically and numerically to try to understand these processes. But, as I said before, observing these now in gravitational waves, in neutrinos, and in electromagnetic waves will give us a picture that we haven't obtained before. And just looking ahead in the future, LIGO in the US, Virgo in Europe, Kagura in Japan, and in a few years' time, LIGO India will be working with next generation optical telescopes like the Large Synoptic Orbit Telescope. And when these type of observatories join forces, then we are going to be making discoveries at a latency, at a scale that will be overwhelming for existing infrastructure and approaches. And it is this type of work that I do in my group, combining artificial intelligence with high performance computing, that will, open the gate to process this data in real time at the scale and then extract all the science that we can with this large amount of observations that we will have in just 5 years down the road. So it is certainly going to be a really exciting time. And seeing the convergence of these different fields, astronomy, physics, computer science, software and data, and obviously policymakers, is preparing a scenario that is going to be really exciting to be part of.
Does the existence of gravitational waves open the door for the possible existence of other types of waves? Now that we've verified that they're real and they're there, are there other places now we can look that we didn't look before to try to find other types of phenomena?
Yes, and that's an excellent question. Every time a new discovery is made in a new spectrum of observation, new discoveries happen. And so what we now know is that black holes exist for real. They are astrophysical entities. We also know that they form binary systems, two objects orbiting around each other, and that they coalesce within the age of the universe. This is something that we did not know. And now the next question is, all right, we can see these black hole collisions. What if we now go and see a signal, a type of gravitational wave that is not predicted by Einstein's theory? What are the implications of this discovery for our understanding of the formation and evolution of the universe? Because we use general relativity to model how the universe has evolved in cosmology. So if we just happen to make this type of breakthroughs in the next few years, it is going to have repercussions in every single field: stellar evolution, cosmology, formation of large scale structure in the universe. So, this is a new field of study, and we just are waiting to see what new implications upcoming observations provide.
Can you tell the age of a gravitational wave, meaning when the collision happened?
Absolutely, yeah. We can estimate um, about the distance to the source, and with a cosmological model, we can infer when that collision happened. Yes, that's right. And it is this is also the connection to cosmology, because we have been using supernova to estimate how fast the universe is accelerating in its expansion. But now we can use black hole observations. If we can infer where the galaxy that hosts this event is located, we can estimate the distance to it and then infer the Hubble constant. And the difference is that with supernova observations, we can only study this in the nearby universe. But now with LIGO, we can go to distances up to which the universe was about half of its current size. So we can now explore the expansion of the universe up to really high values of redshift. And then, with the cosmic microwave background, we can study this in the very early universe. And now we are getting finally the ability to make this type of measurements in a completely unknown regime. And it just happens that with one of our black hole observations, we estimated the Hubble constant. And you may know that there is right now a discrepancy in the Hubble measurement when you use the CMB and supernova. And it just happened that the measurement with gravitational waves was right in the middle of the two predictions. And so I expect that in the near future, with more observations of this nature, we will be able to really understand, what is the favor measurement, and what is the new physics that this implies if there is actually some tension between these two independent probes that we use.
Are we able to deliberately try to look as far out as we can go, and then maybe see an incoming gravitational wave that would let us, quote unquote, see beyond the observable edge of the universe, or back to a time that is before any previous time observed?
So this is the issue with a very early universe, right? Right now we are using light, which is the
Right.
electromagnetic waves. If we, for example, were able to use the primordial gravitational waves, that would be a completely independent probe to study this type of phenomena. So that is also a possibility. No longer use the cosmic microwave background, but now use the primordial gravitational waves. And people are looking for them in the data. So that would be a possibility. And let me just tell you, we were talking about LISA, right? This space-based uh, gravitational wave observatory. It will be able to see events up to a quantity we call redshift of 20, which is very early in the universe. So there you have, with LIGO, you go from redshift basically in the nearby universe, very close to zero, all the way to about redshift of 1. And then with LISA, you will take it from there all the way to redshift of 20. It's going to be amazing. And then if you are able to observe these primordial gravitational waves, then you will be in a similar regime to what you can obtain with the cosmic microwave background.
Okay, yeah, that's what I was wondering, if they would let us see in a different way that didn't involve lights. That's why I was asking. So
Yeah.
well, very good. So we're running out of time, but this has been really interesting. What's the best way for people to get in contact or ask questions or see some of the work of the things you've been doing?
Yep, sounds good. And thanks a lot for the invitation.
Oh yeah, no problem. What's a good website or a place for people to go to find out more?
Well, if they go to gravity.ncsa.illinois.edu, there they can see things that we're doing in our group. It's gravity.ncsa.illinois.edu. And if they also go to just the NCSA website, ncsa.illinois.edu, they can also see the research that we're doing in the center that spans many different fields, from industry, agriculture, medicine, visualizations, the study of the universe with numerical relativity, cosmology, large-scale astronomical surveys. It is a very rich department with interests across the spectrum in different science domains.
Okay, well, very good. Well, Eliu, thanks for coming on the podcast. I appreciate your time.
Sure, thank you.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.